This presentation is devoted to energy demand and supply with focus on the topic of Zernez. Starting to look at it from a global perspective, the built environment is generating nearly 40% of the annual CO2 emissions. Keeping that in mind that approximately 2/3 of the building area that exists today will still exist in 2050. So the question is, what do we want to do? Especially thinking that currently building renovation affect only 0.5 to 1% of the building stock annually. So a significant increase in the rate of existing building energy efficiency and renovations is critical to meet our objectives to get to a zero CO2 emission environment. Looking at specific Swiss buildings, today in Switzerland, we are importing roughly 325 petajoule annually, just for the Swiss building stock. We do already have 71 petajoule per year on renewable energy, and the two together lead to 25 tons of CO2 emissions. Our objective is to have a CO2 reductions by a factor of 3, which would then mean the energy import is being reduced to 110, while the renewable energy portion is increased to 130, then generating CO2 emissions of only 8 million tons, which is only about a quarter of what's happened today. Therefore, we are addressing existing buildings in a two-step approach. First, reducing the energy demand, which can be accomplished by renovating buildings and respectively the envelopes, keeping the warmth inside the building, while for new buildings we apply higher standards. For the use of energy, we are more conscious and change and adapt the processes. One example is a simple fact of boiling water. Boiling water in a pan is requiring 3 times as much energy than boiling water in a tea kettle, just as one of the examples where the effect of water boiling is identical, just the use of energy has been reduced by 1/3. Whatever is left as a requirement for energy is to be done in an efficient way, applying new technology and building on renewable energy. Looking at the energy demand of Swiss residences, we can see that 2/3 is required for space heating. Obviously, this is partially of the low winter temperatures, but in addition to that, we require almost 15% for heating of hot water, and then another 1.8% for heating, ventilation, air conditioning, making together the majority of the energy requirement in Swiss residences. A perfect way to reduce the energy demand of buildings and reduce the space heating requirement is to do an insulation, so a packaging of the building. Now, given that the buildings in Zernez are very pretty and therefore Homeland protected, one cannot do an insulation from the outside. So therefore, it needs to be done from the inside, as can be seen on the right-hand side, to have a similar effect. While not as efficient, it may take a little more material, but it satisfies both the energy requirement and the homeland protection and policies. So moving to the energy supply, one technology everyone has been talking about is wind power. Now, wind power not only requires certain winds, but it also requires the acceptance of the habitants, which in the case of Zernez is not an option. So therefore, wind power is not part of this simulation. Solar energy is the most obvious source of renewable energy. The sun is shining around the world more or less intense. Looking at selected areas like the UAE on the lower left-hand side, we can see that the horizontal irradiation reaches levels of 2,500 kilowatt hours per square meter. In Switzerland, just like in Japan, the level is around 13 to 1400 kilowatt hours per square meter and year. And zooming in more specifically on Zernetz, we can see it is in a fortunate region within Switzerland, exceeding even 1400 kilowatt hours per square meter and year. Solar energy can be captured using photovoltaic technology, where solar radiation is being converted directly into power. Such PV, as we call it, so photovoltaic modules, can easily be mounted on top of the roofs as shown here. If space permits, those PV panels can be mounted freestanding as one of the options for Zernez to be considered. One effective way to heat a building is using and applying heat pump technology. Heat pumps work like refrigerators. They cool one side and heat another side. So like in the refrigerator, we all know that when we're touching the back of it, we have a heat exchanger which is warm. So this concept is being applied to buildings whereby there is heat extracted from the ground or any other source of low temperature heat. Then there is compressor electricity being added, and then the heat is pumped, as the name says, to a higher temperature level and then supplied to the building, which in case of the refrigerator is the backside of it. In this graph we can see then how the heat exchanger is being put into the ground to absorb heat, and then how it is distributed through the building for heating purposes and hot water. Now, here we see the challenge. We can have photovoltaic on the roof, maybe even a windmill somewhere. We need to worry about hot water, and all inside the building where we know that it's a challenge to only use heat when the sun is shining. If we could pool multiple buildings together, we have a better chance to avoid simultaneous requirement. For example, it is unlikely that everybody is taking a shower exactly at the same time or making dinner or lunch at the same time, while then maybe energy storage can be a good option and is therefore favoring a decentralized energy system. District heating system is including a biomass wood chip heating plant. In this plant, the biomass is burned effectively and efficiently, heating water to be circulated for the heating system. The remaining exhaust air is then effectively filtered to not harm the environment at all. So hot water is circulated through the district heating pipes, which are being put into the ground sufficiently deep to not cause any freezing during non-operation. At the same time, it is insulated to minimize heat losses. When the water gets to the individual houses, there is a transfer to a separate loop, which is circulating water inside the building, providing heat in the rooms through radiators, and providing hot tap water also generated by this district heating system. In a cogeneration heating power plant, the burning wood chips, for example, are first heating the return water, and which is then being warmed up further in the final heat exchanger. At the same time, in the burning cells, pistons are operated to drive a generator. Thereby, the energy balance overall looks at 30% of the input energy is being exited as electricity and 50% as heat, making it quite an efficient system. Mentions the piston. It is evident that the equipment itself looks like an engine, which it in turns it is, which you can see in the foreground, a generator, which is a very effective way to provide electricity to the system.